So here we've got two flow pipes that are, one of them is twice as long as the other, but they're otherwise identical. And if one of them is twice as long, what does that immediately suggest?
I think it suggests that the resistance of the pipe is going to be twice as much as the other one.
Yeah, so let's call these pipe A and pipe B. Let's say pipe A has resistance R and pipe B has resistance 2R.
And that resistance applies to the entire pipe, right?
In the sense, actually, let me call this RA, and then RB equals 2 times RA. Yeah, the resistance is a property of the whole pipe in the sense that it only applies if you're looking at the whole thing. If you look at just a smaller section of the pipe, then that'll have a smaller amount of resistance. Or if you were looking at like two pipes joined together end to end, the resistances would add together. So the RA and RB being 2 times RA, that applies to the length of the resistance of the whole pipe altogether. And if the resistance is twice as much, but what do we know about the pressure difference for the whole pipe?
Isn't it the same?
Yeah, they should both experience the same pressure drop because they both start from the same high pressure, presumably from some pump or something. And they both end at the same low pressure. Specifically, what pressure do they end at?
Atmospheric pressure.
Yeah. So they both start at the same high pressure. They both end at the same low atmospheric pressure. That's true for both pipes the same way. So both pipes experiencing the same delta pressure. And we can then use that to, in conjunction with the Bernoulli equation, to figure out the current. Because if you're going from end to end, from the beginning of the pipe to the end of the pipe, or from the beginning of pipe B to the end of pipe B, in either case, what are the only terms you would need to include in the Bernoulli equation?
I and R and delta P, maybe?
Yeah, because we've got a delta pressure. There's definitely a difference in pressure from start to finish. We're going from high pressure at the beginning to low pressure at the end. There's no difference in height from start to finish because the whole pipe is level. In fact, it doesn't even have to be the whole pipe. Just the beginning and end are at the same elevation. So there's no delta Y. The pipe has the same cross-sectional area at beginning and end. So there's no delta speed. We just have delta pressure equals, and there's no pump in between. So all we've got on the other side is negative IR. Which means if you solve that for current, what do you get?
Is it delta pressure over negative R?
Yeah, that should work. Which means if we compare the two pipes, and keep in mind this delta pressure and this R are talking about the whole pipe.
Okay.
So if you look at the delta pressure for the entire pipe A and the delta pressure for the entire pipe B, what do we know about their delta pressures?
They're the same.
Yeah, same delta pressure, but what do we know about the resistances?
The resistance in pipe B is twice that of A.
Right, so if we're dividing by twice as much resistance, what does that tell us about the resulting current?
It's half as much.
Yeah, pipe B has twice as much resistance and thus half as much current. So the current in pipe B is flowing half as fast as the current in pipe A. Any questions on that so far?
No, I'd get that much so far.
Okay. And then in part C, we're looking at the water levels, which, as we mentioned earlier, really represents the pressure at the bottom. The height to which water rises in a standpipe, or any fluid really, the height to which fluid rises in a standpipe represents the pressure, the gauge pressure at the bottom of the standpipe. So if we start with, it looks like it gives us the pressure levels at pipe A. And instead of writing those in terms of pascals, we could basically treat tick marks in the column, in the standpipe, as a de facto measurement of pressure. For instance, in the first standpipe, that looks like 6 tick marks. So let's say the pressure at point 1 is just 6 tick marks. And of course, that could be converted to pascals if we know how far 1 tick mark is. But we can essentially use tick marks of water as a measurement of pressure. So at the first one, pressure is 6 tick marks. Also, what do we know about the beginning of pipe B?
It has the same pressure because it's coming from the pump or whatever, the faucet, as pipe A.
Exactly. Pipe B starts with the same high pressure that pipe A did. So that means the first standpipe is still that high pressure. So that first standpipe is also going to be 6 tick marks. So we can assume this one fills up to 6 tick marks. So that'll be 2, 3, 4, 5, 6, something like this, filling up to 6 tick marks. And then for the next step, what we really need to look at is the changes. We want to know how much does the pressure change? Because what we can consider here, if instead of looking at the whole pipe, let's take a look at just this section of pipe. Because what we care about is how far we're going to the next standpipe. So from the first standpipe, high pressure of 6 tick marks, to the next standpipe, what would the Bernoulli equation look like for just that section?
We'd have delta P and the IR.
Yeah, we're also going to have delta P equals negative IR. But in this case, are we talking about the whole pipe?
No.
So that means we're not going to be using the full 2 times RA. We're using just the resistance of this section. So delta P for just that section equals negative I times resistance of just that section. The current is the same at every point in the pipe, though. So we're still going to use that same current for the whole pipe. If we compare that, though, what's a corresponding section of pipe A, which we do know about pressure, that would have the same amount of resistance?
Wait, so when we calculated in part A, that does not apply to the entire pipe, is what you're saying? So that 2 times RA, you can't use that for the whole thing?
2 times RA is the resistance of the whole pipe, in the sense of, like, let's say this pipe is 6 meters long. 2 times RA would be the resistance of the 6 meter pipe. But if you're looking at just, let's say, 1 meter of that pipe, that doesn't have the full resistance.
Okay.
Resistance depends on length. So if you take 6 meters of pipe, that has a certain resistance. If you only take 1 meter of pipe, that would only have 1/6 as much resistance as the 6 meters of pipe, because resistance scales based on length.
Okay.
So when we say the resistance of the whole pipe, we don't mean each piece of the pipe has that much resistance. We mean the whole pipe taken as one big object has that much resistance. But if you split it up into smaller pieces, the smaller pieces have a smaller amount of resistance each.
Okay.
So what we can compare that to, and really we want to compare this to pipe A, because we know the pressures in pipe A, 6 tick marks, and then it looks like 3 tick marks and 0 tick marks. Let me fill those in. So we know the pressure at these 3 labeled points on pipe A. Is there a portion of pipe A that's going to have the same resistance as this portion of pipe B?
You would think it would be the 3 one, but I feel like it's not that one.
What do you mean the 3 one?
The one with 3 tick marks, because it looks like the same length there.
Well, in terms of that section of pipe, yeah. This length of pipe from the beginning to the next standpipe is the same length as from the beginning to the next standpipe. So let's say this is a certain distance. Let's just call that distance delta x. If we mark off the same length on both pipes, and ignoring everything else, if we just ignore the rest of the pipe and focus on just this section, these two sections of pipe are identical. They're the same cross-sectional area because it's the same kind of pipe, same material, same viscosity of fluid, and same length. Because we're marking off, I don't know, maybe 5 centimeters of this pipe and 5 centimeters of this pipe or something. So what can we say about the resistance of this section of pipe and the resistance of this section of pipe?
It should be the same.
Right, they have exactly the same resistance. So this section has resistance, let's say R sub S, resistance of one section. And this section also has resistance R sub S. So going back to the Bernoulli equation, the delta pressure for just that section, from pressure at the start of that section to pressure at the end of that section, should be negative current times resistance of just that section. These two sections have the same resistance because it's the same length of pipe. But what do we know about the current in this one and the current in that one?
The current in B is half as much as A.
Right. So going back to the Bernoulli equation, delta pressure in that section of B is going to be negative half as much current times the same resistance. If these two sections have the same resistance, but one of them has half as much current, what does that tell you about the pressure drop?
It'll be half.
Right, half as much drop in pressure. Because the current's only flowing half as fast, so we're losing pressure at half the rate. Which means we really should be considering the drop in pressure, the pressure change. So if we consider the change in pressure from the first standpipe to the second standpipe, what's the change in pressure from beginning to the next standpipe in pipe A?
3.
Yeah. Or since it's a decrease, I would call that -3. So delta pressure is -3 tick marks. So half of that would be what?
-1/2.
Yeah. From here to here, delta pressure would be -1.5. So that's how much pressure we're losing. And we started at 6 tick marks. If we lose 1.5, what are we now at?
4.5.
Yeah, so that would be the pressure in the second standpipe, 4.5 tick marks. So we could draw the water in that one rising up to 4.5 tick marks.
Wait, but if we're using that equation and it's delta P and it's -1/2, won't you like times both sides by 2 to like cancel the -1/2? Like, so it's the same for A and B? Like, how mathematically can you show me how we get the 1.5?
Yeah, if we have delta pressure in the section of pipe A is negative current in A times resistance of just that section. And we happen to know that that equals -3 tick marks. If we compare this to B, delta pressure in this same section of B is going to be -IB times resistance of the section, which is the same. But what do we know about current B?
It's 1/2 current A.
Right. So if we replace current B with 1/2 current A, we also know that if we combine current A times resistance of the section, negative current A times resistance of the section is -3 tick marks. So we can make that substitution. Negative IA times resistance of the section is -3 tick marks. But this divided by 2 turns it into -1.5 tick marks.
Okay, I see it where you got it now.
So that's our delta pressure for just that section. Any other questions on those standpipes so far?
Nope, good so far.
And then if we take a look at the next section, this section is the same length from the second standpipe to the third standpipe. So it's going to be identical. It's the same length, so it's the same amount of extra resistance. So we're going to be losing the same -1.5 tick marks. We can use the exact same procedure, and you could run the calculations again, but comparing it to maybe the second section, but it's identical. So it should lose another 1.5 tick marks, taking us down to 3 tick marks. So that'll be the new pressure, and it'll only rise up to 3 tick marks instead of 4.5.
I get it now. Thank you.
Mm-hmm. And also, if we went another section, let's say we had a fourth standpipe here, that would only rise up to 1.5. And then another section, we get down to 0, which we should expect because at this point we're open to the air. So our gauge pressure will be 0. The water doesn't rise at all in the final standpipe if there was one, because there's no difference between the pipe pressure and atmospheric pressure.
Got it. Thank you.
You're welcome. Any other questions on the standpipe stuff? Okay, then let's take a look at some fluid circuits. Let me set up a new one here. So if we're talking about a fluid circuit, what does that mean? What should we expect to find in a fluid circuit?
Like a fluid system that's connected.
Yeah,
to start
maybe some pipes or something that connects back to itself. The simplest example would be just like a single loop. We've got a loop of pipe, and presumably we're going to have a pump in order to get things moving. So let's say we've got a single loop and we've got a pump. What does a pump provide?
Increase pressure on the direction of the flow.
Yeah, so we can describe that as the work density of the pump. Work density of the pump, and let's say we know that value. Let's say that's 200 pascals, or you could also write that as joules per cubic meter. And the advantage of a fluid circuit is instead of looking at the Bernoulli equation from a single location to some other location, we can just pick some starting location. Let's say this corner right here. Let's call that location number 1. But instead of going from location number 1 to some other location, we could talk about the path from location number 1 all the way around the loop, because we have a complete loop, and back to point number 1 itself. So instead of talking about the Bernoulli equation from location 1 to some other location 2, we can talk about the Bernoulli equation for the complete cycle from 1 to itself. And in that case, if you're going from 1 to itself, how much delta pressure is there?
None.
Right, there's no delta pressure because we're starting at pressure 1 and we're ending at the same pressure. And also, what can we say about height?
No change.
Right, even though there might be changes in between, point 1 is at the same height as itself. So there's overall no delta Y. And same thing with speed. There might be changes in speed in between due to changes in cross-sectional area. But if we return to the starting point, there's no change in speed either. All of the deltas are going to be 0 because we've returned to the starting point. So all that's left in the Bernoulli equation would be what?
The pump and the thermal energy.
Right. So the entire left side is going to be 0 because all the deltas are 0. On the right side, we have work density of the pump and also minus I times R. So that's the simplified Bernoulli equation for a complete circuit. All of the deltas are 0 because we've returned everything to the starting values. But along our path, we have gone through a pump and we've gone through some pipe that presumably has resistance. And I think this is an important thing to consider for the Bernoulli equation. The left side of the equation, all the delta stuff, any delta is talking about the difference between initial and final values. So that just cares about start and finish. It doesn't care about the path. If start and finish are the same, then all those deltas will be 0. But the other side of the equation, the work density of the pump and the minus IR, those are talking about what's in between, what's along the path you're taking. So for that side of the equation, you want to consider as you travel along that cyclic path, are you going through any pumps? Are you going through any pipe with resistance? And let's say we do know the resistance of this pipe. Let's say we know that the pipe overall, this loop of pipe has resistance. Let's say we happen to know that the resistance is 50, what are the units for that? Pascal meters cubed per second, no, Pascal second squared per meter cubed, I think. Sorry, Pascal seconds per meter cubed. So let's say that's the resistance. We happen to know the resistance is 50 Pascal seconds per cubic meter. Maybe we know that this type of pipe has a resistance of 10 per meter, and we know that it's 5 meters long. So you can calculate the resistance if you know the type of pipe and how long the pipe is. In that case, what else can we now solve for in the Bernoulli equation?
Current.
Yeah, we can isolate current in this equation. Since we know the work density of the pump, that's given, and we know the resistance, that's given. So we could isolate I. And if you isolate I here, what would you get? Or how would you isolate I in this equation before we even fill in any numbers?
Add the or subtract the work from the pump to the other side and then divide by R.
Yeah, or in that case, you'd want to divide by negative R. So yeah, you'd get the work density of the pump divided by the resistance, which suggests, I mean, before we even plug in any numbers, this suggests that a stronger pump is going to lead to more current and more resistant pipe is going to lead to less current, which is what we should expect since resistance represents essentially the difficulty level. If we fill in these numbers, 200 pascals divided by 50 Pascal seconds per cubic meter, what do we get?
For, I don't know the units.
Yeah, well, 4 is correct numerically. As for the units, what's going to cancel out here?
Pascals, I think.
Yeah, because we've got pascals in the numerator and pascals in the denominator. That leaves us with seconds per meter cubed, but it's in the denominator. So you'd have to invert that and get what?
Meters cubed per second.
Yeah, which is what we should expect for current, which ultimately just means that I did correctly remember the right units for resistance. Any questions on that fluid circuit so far? Then let's take a look at a slightly more complicated one and see what we can do. Let me clear this one. Let me draw out a different circuit. Let's say we've got a pump. And some pipe. And let's say the pipe splits. Let's say we've got this narrow section of pipe and this other narrow section of pipe. And let's say that the wide pipe is so easy to flow through, it has no resistance. But the narrow pipe sections do have resistance. Let's say those narrow pipe sections have resistance. Let's call this R1. Let's say that's, let's say 4 Pascal seconds per cubic meter. And let's say the other one has resistance 2, which is, let's say 6 Pascal seconds per cubic meter. So let's say those resistances are known. And also let's assume this is a top-down view. Like this whole thing is just flat on a tabletop, so there's no differences in height. That way we don't need to worry about potential energy density. If we are looking at, if we want to find the current here, can we draw a single loop that will make this work? For instance, let's call the point right before the pump, let's call that location 1 again. Can we draw a loop from 1 to 1?
There's 2 loops you could draw.
Yeah, we could draw from 1 through the pump. Narrower. From 1 through the pump and through one of the resistors. But we could also draw another loop from point 1 through the pump and through the other resistor. So we could actually write out the Bernoulli equation twice, one for each of these loops. So for, let's say, the upper loop, the loop going through the pump and resistor 1, we could use the Bernoulli equation. The overall, since we're starting at 1 and ending at 1, there's no change in any of the delta whatevers. But we've got work density of the pump. But I should probably include that information also. Let's say we know that the work density of the pump happens to be, let's say, 120 pascals. So if we write this out the same way, work density of the pump minus I times R. And we solve that for I. That'll still be the same work density divided by R. But if we fill in these values, the work density and the resistance of just pipe 1, what are we going to get?
What was the question again?
If we fill in the work density of the pump and the resistance, but for this, just this upper loop, so ignoring the lower loop entirely.
Like 120 over 4?
Yeah. This loop, the only resistance we're passing through is narrow pipe number 1. So we get 120 for the work density of the pump divided by 4 for resistance 1. So 120 over 4, that'll be 30 meters cubed per second. But if we try that for the lower loop, if we ignore branch 1 and look at just the current through the lower loop, then we get the same Bernoulli equation in terms of the variables. We're going through a pump and we're going through a pipe with resistance. However, we've got a different amount of resistance. So when you solve this for current, what do you get?
20
yeah.
meters cubed per second.
Right, 20 cubic meters per second for that current. So these two pipes get different currents. In fact, the 30 cubic meters per second and 20 cubic meters per second, that really represents the current through just that branch. So this branch is getting a current of 30 cubic meters per second. Let's call that I1. And then the lower branch is getting a current of 20 cubic meters per second. So we'll call that I2.
Question?
Yeah.
Wouldn't the current change, it'd be different in the wider pipe before it goes to the junction? So how come like calculating the loop gives you just the current of the small section?
Because the IR here, what's the only part of this that has resistance that we care about?
Oh, the narrow part.
Right. So the current that's used in the equation is specifically the current in the section that has resistance.
Okay.
If the wide pipe has no resistance, then the current through it doesn't really matter in the sense that it doesn't show up in the equation. We would care about it if the wide pipe did have enough resistance to worry about. And realistically, every pipe has resistance. But if the pipe is very wide or very smooth or not very long, then we can assume its resistance is small enough to not really matter very much. In this case, though, if we only are considering resistance in these narrow pipes, then we would say that the current that we're talking about that's being multiplied by resistance of that pipe is just the current in that pipe. However, if we take a look at those pipes coming together, if we have 20 cubic meters per second flowing this way, and also 30 cubic meters per second flowing this way, what happens to those currents at the junction here?
They add together?
Yeah, those are going to add together, and we're going to get how much current flowing through the pump itself?
50 meters cubed per second?
Yeah, those currents combine to 50. So the current through the pump, and we would usually call that I sub 0, is going to be 50 cubic meters per second. And this is ultimately just from the continuity principle. If you consider this section of the pipe, you've got 30 cubic meters per second and 20 cubic meters per second flowing in. Those add to 50. So you've got to have 50 cubic meters per second flowing out the other end. So we now know the current flowing through the pump is 50 cubic meters per second. Any questions on that so far? And a couple of the things about this that are useful to consider. Have you seen the idea of how you would combine resistors in parallel?
Like the inverse?
Yeah.
Like 1 over R equals 1 over R1 plus 1 over R2.
Yeah, if we want to know the total resistance of this circuit, we can use that idea of adding the inverses, adding the reciprocals. So instead of just adding 4 plus 6 for the resistances, we're going to say 1 over the total resistance equals 1 over R1 plus 1 over R2. And mathematically, how would you add 1 over 4 plus 1 over 6?
Would it be 5/12?
Yeah, because the 12 is a common denominator there. 1/4 is 3/12. 1/6 is 2/12. So that is 5/12. So does that mean 5/12 is the total resistance?
Wouldn't that be 1 over? So would the total resistance be 12/5?
Exactly. We got to invert both sides. Our total is going to be 1 over that. So 12/5. And the units will still be Pascal seconds per cubic meter. So this whole thing, these two resistors in parallel, act like one pipe with resistance 12/5, which means we can draw a simplified version of this circuit. We can say this circuit, this whole thing acts like a simpler circuit, which we could draw as the same pump. We don't need to simplify the pump itself. And just one single pipe. And we can say that that pipe has the effective resistance, the total resistance of 12/5. So in that case, if we also fill in the work density of the pump, which we know is still 120, how would we then find the current in this section, in this circuit, this fluid circuit?
Use 0 equals E pump over volume minus IR equation.
Right. And once again, we can isolate I and get work density of the pump divided by resistance. In this case, we'd be using the total resistance. So we've got 120 pascals divided by 12/5 Pascal seconds per cubic meter. And if you take 120 divided by 12/5, what do you get?
Uh, 50?
Yeah. 120 over 12 reduces to 10. Divided by 1/5 is times 5. So you get 50 meters cubed per second. And that's exactly the same as what we got for the current through the pump, analyzing it this way. So either of these methods, either analyzing each loop separately and then adding the currents to get the current through the pump, or combining the resistors in parallel and treating it as a simplified circuit, also gets you the same current through the pump. Any questions on that so far? And speed, you mean like the speed of the fluid? If you wanted to know speed, you would also need to know the cross-sectional area. So as always, you can just use the idea that current equals speed times cross-sectional area of the pipe. So we know the current everywhere now. If we also knew the area in each section of pipe, we could just divide by area to find the speed in that section of pipe.
Isn't the current, you'd have to use a specific current for that section, right? Like if.
Right.
Okay.
Because speed is really unique to that location in the pipe. So for instance, if we know that the current in this section of pipe is 30 cubic meters per second, if we also knew the cross-sectional area of that region of the pipe, we could solve for the speed in that section of the pipe. And have you gone over the idea of power yet?
Really briefly.
One way to do that in this case, it might be actually useful to look at the units here. We know that the pump is providing 120 pascals of pressure. We also know the current. What is the current here? The current is 20 cubic meters per second. No, sorry, 50 cubic meters per second. So if we combine those, what's another way of writing pascals? If we want to emphasize that it's an energy density can always be written as what over what?
Joules per meter, cubic meters.
Yeah. And that's just same as pascals. Pascals can also be written as joules per cubic meter. If we combine these, if we multiply work density of the pump times current through the pump, 120 times 50, and then the units are going to be joules per cubic meter times meters cubed per second. What happens when you multiply those units? If you got joules over cubic meters times meters cubed over seconds, what's going to happen?
Joules per second.
Yeah, the cubic meters cancels out. We're left with just joules per second, which is the units of power. 120 times 50 is 6,000 joules per second, also known as watts. And that's the power, because power represents the rate at which energy is being delivered. If the pump is providing 120 joules of energy to each cubic meter that flows past, and 50 of those cubic meters flow past per second, that means the pump is delivering 6,000 joules of energy to the fluid per second. In other words, 6,000 watts. And that's really all power means. In physics, power just means how quickly is energy being transferred, amount of energy, joules per second. So we'd say that the power rating of this pump is 6,000 watts or 6 kilowatts. That represents how quickly the pump is delivering energy to the system by pushing on the fluid. And in general, you can calculate the power created, the power provided by a pump by multiplying the pressure it provides times the current flowing through it. You can also do the same thing for a individual section of pipe. If you know the pressure difference, like how much pressure is being lost through that pipe, you can multiply the delta pressure times the current. So in general, power can be found by multiplying delta pressure times current in that section of pipe. Regardless of whether the delta pressure is from a pump or from resistance, that change in pressure, I mean, really it should be change in total energy density. But usually the energy density we care about is the pressure. So in general, power for some section of pipe can be calculated as the change in energy density for that section of pipe times the current flowing through it. That tells you how quickly a pump is delivering energy to the fluid system, or how quickly a resistance is removing energy from the system. Any other questions on that? All right, then I will see you next time.
Thank you.
You're welcome.